GATE 2020 is nearby. So if you're a GATE aspirant, it is really time for you to fasten your preparation because it is happening in February, that is the first week of February. And if you're an electronics student, if you're preparing for electronics GATE exam, the analog circuit is the area you need to really concentrate, because if you see the exam pattern, that is the mark division of GATE 2020, the maximum mark division is given to analog circuit portion. Okay, so you need to really concentrate on analog circuits, and this video we are going to cover the analog circuit topic. We are going to discuss various topics, various questions from the analog circuit topic. So let's see. First question which we are going to discuss today is this: when do loading effect occurs in the below circuit? So this is the below circuit. Now the options given are option A, when R2 is small, option B, when A1 is small, option C, when R2 is large, option D, when A2 is large. So this circuit, if you examine, it is nothing but the cascading of amplifiers. So in analog circuit, we have studied the topic called cascading of amplifiers. And here, when you're cascading two amplifiers, there are two amplifiers, there are two voltage values, that is V1 is the input, V0 or VO is the output. There are two resistors, R1 and R2. R1 is the output resistor of this particular amplifier, and R2 is the input resistor of this A2. Now, when do this loading effect occurs in cascaded amplifiers? When there is a connection between the two amplifiers, that is when the input resistance of the second amplifier or the nth amplifier is lesser, it is having a loading effect from the n-1th amplifier or the previous amplifier. So what happens in this case is the voltage gain of this amplifier will get reduced. So when the two amplifiers are cascaded, and if the resistance R2 or the input resistance of next amplifier is less, the voltage gain of the previous one will get reduced. And due to this, there is an interaction between these two amplifiers, and this effect is called the loading effect. So here we have to use a high valued R2 to reduce the loading effect. So when we are using a high valued R2, that means these two amplifiers will be non-interacting amplifiers. Okay, so here the correct answer is option A, that is R2 is small. So when R2 is small, what will happen? Loading effect will occur. The next question which we are going to discuss is this: in the circuit shown using ideal op-amp, the 3 dB cutoff frequency in Hertz is dash. So this is a circuit, and the options given are option A, 159.15 Hertz. So the value should be in Hertz. B, 154 Hertz. C, 240 Hertz. Option D, 200 Hertz. So if you examine this circuit, this is a ideal op-amp circuit. So you have to think of the features or the characteristics of ideal operational amplifier or op-amp. And also if you examine this, you can see the input or the VI is given to the non-inverting terminal of the op-amp. So this is a non-inverting op-amp. So this op-amp is having a feedback resistance of RF. Okay. So you can redraw this circuit in order to make this a little more clear. There is a resistor here. There is another resistor. There is a non-inverting terminal. Now, to the inverting terminal, there is one resistor connected. Now, what I'm going to do is, so an input is given. So this capacitor is again grounded here. So again, anyway, it is connected to this ground, right? So I'm giving a separate ground for this capacitor. Now there is a feedback resistor connected to the output. So this is output, this is the inverting terminal. So this value is 10, this value is 10, nothing but 10K. 10K, this is also 10K. The capacitor value is 0.1 microfarad. Okay, in order to make it a little more clear, I've just redrawn the circuit with the capacitor having a separate ground. Okay, So it is same as that of this. Now if you see this, you can understand that the input is connected to which terminal? That is the positive terminal or the non-inverting terminal. And in the case of an ideal op-amp, the ideal op-amp has a characteristic that it doesn't draw any input current. That is, this input current means current to the positive terminal. So there are two terminals, positive terminal and negative terminal. So since the ideal op-amp doesn't draw any input current, means here there is no current drawn to this point or this input. So there is no voltage drop across this 10K resistor. So that thing you have to keep in mind. Since there is no current drawn to the input, there is no voltage drop across this 10K resistor. So the voltage here, that is, let it be V plus. The voltage is same as that of the voltage here, because since there is no voltage drop across this resistor, the voltage, whatever the voltage be here, it will be same as here also. Now, let us consider this circuit or this portion of the circuit. So there is a resistor and there is a capacitor connected to it, right? This is nothing but a low pass filter. So this connected in parallel with a resistor is a low pass filter. Okay, so this is a low pass filter, right? The value of the resistor is 10K and the value of the capacitor is 0.1 microfarad. Okay, now what is the cutoff frequency for a low pass filter? Cutoff frequency means the frequency to which it will pass. That is, a low pass filter will pass only low frequencies and it will cut off or try to trim off the higher frequencies, right? So that is the function of a low pass filter. So what is the cutoff frequency of a low pass filter? So the cutoff frequency of a low pass filter is given by fH equal to 1 by 2 pi RC. Here the value of R is this resistor value, that is 10K, and the value of C is 0.1 microfarad. So you have to substitute the values of R and C here, that is 2 into 3.14 into R is 10 into 10 raised to 3, that is 10K, into 0.1 microfarad is 0.1 into 10 raised to minus 6. And if you solve this, you will get 159.15 Hertz. So this is the 3 dB cutoff frequency of this operational amplifier. So the next question which we are going to discuss is this. For any cascaded amplifier network, which of this is incorrect? Option A, cascading increases gain. So we have already done a question on cascading of amplifiers. So cascading, whether it increases gain? Yes, obviously it increases gain. So the first option is cascading increases gain. Second option is overall input resistance is equal to the input resistance of first amplifier. So here in the case of cascaded amplifier, we know that the input resistance is equal to, that is the overall input resistance is equal to the input resistance of the first amplifier. Third option, the overall output resistance is less than the lower output resistance in all amplifiers. That is, if you compare the output resistances of the amplifiers, the overall resistance will be lesser than the lowest value of that. So that is not right, because in the case of cascading of amplifiers, the output resistance is equal to the output resistance, that is the overall output resistance is equal to the output resistance of the nth amplifier, that is the last one. So this one is wrong. D, loading effect occurs, that we have already seen why loading effect occurs and how. So the correct answer for this question is option C, because this is an incorrect statement. So the overall output resistance is less than the lower output resistance in all amplifiers is wrong, because the output resistance is equal to the output resistance of the last or the nth amplifier. So the correct answer for this question, that is, we have to find the incorrect statement, right? So the correct answer for this question is option C. Next question is, it is given that the lower cutoff frequency of an individual amplifier is 25 Hertz. Find the net cutoff frequency for a cascaded network of 8 amplifiers. So this is also from Cascaded Amplifiers. So this question is also from Cascaded Amplifiers. So here we are going to cascade 8 amplifiers. So the value of N is 8. That is, we are going to cascade 8 amplifiers. So N is 8. And also it is given, that is FL1 is given as 25 Hertz. FL1 is nothing but the cutoff frequency of individual amplifier. So if the cutoff frequency of individual amplifier is given, then the net cutoff frequency FL equal to FL1 by square root of 2 raised to 1 by N minus 1. So this minus 1 is outside the square root. So here you are given both N and FL1. So what you need to do is you have to just substitute the value here and find the answer. So here it is 25. The value is given in Hertz. So 25 by 2 raised to 1 by 8 square root minus 1. So this will give you your result. And if you solve this question or this sum, the result obtained is 83 Hertz. So this is actually a very simple question. You just have to find or understand this formula for finding the net cutoff frequency while cascading amplifiers. So first you need to find out how many amplifiers you are going to cascade. Also how to obtain the net cutoff frequency, that is using this equation. And here the individual cutoff frequency is FL1, which is equal to 25 Hertz. So the correct answer here is option B, which is 83 Hertz. The next question is DC average current of center tapped full wave rectifier is dash. You have to give the DC average current of the full wave, that is a center tapped full wave rectifier. Option 2 Im by pi, option B Im by pi, option C Im by 2 pi, and option D 1.414 Im by pi, where Im is the maximum peak current in input. So the DC average current means the average current in the output. So what a rectifier is doing is it's nothing but converting AC to DC. So we'll be doing a video on rectifiers very soon. So here they are talking about center tapped full wave rectifier. So it will look something like this. So in the input, there's a primary. You're going to give your AC value here. This is your secondary of the transformer. There is a diode here, there is another diode here, and there is a center tapping. That's why it is called the center tapped full wave rectifier, right? So this is your load resistor across which you'll be getting your output, so which is nothing but your DC output. So in the case of this center tapped full wave rectifier, so you can see there is a center tapping of the secondary coil of the transformer, right? So here there is 2 diodes, and each diode in the case of center tap is going to give us Im by pi current. So this diode will be producing a current of Im by pi, and this diode is also going to produce a current of Im by pi. So the average current at the output is 2 Im by pi. Also for a center tapped full wave rectifier, if you are going to give a full sine wave, only 1/2 of the cycle is repeated. So this is the output of a center tapped full wave rectifier. Okay, so here output current, that is a DC average current at the center tapped rectifier, the output of the center tapped rectifier is nothing but 2 Im by pi. Next is a question of implementing of logic gates using diodes. So here, which logic gate is implemented here? Okay, so there are 2 diodes and 2 inputs are given. There is an output. So there is a load connector 1K. And which logic gate is implemented here? Options are option A OR gate, option B AND gate, option C NOT, option D NOR gate. So we have to forward bias the diode in order to get our output. So if E1 and E2 are digital values, that is 0 or 1, that is we are going to apply either 0 or 1 as E1 and 0 or 1 as E2. So whenever it is 1, we are going to forward bias the diode and we'll be getting the output. So if either of this E1 or E2 is 1, the diode will be forward biased and it will conduct, right? So when either E1 or E2 is 1, we'll be getting the output, and such a gate is called a OR gate. That is, if either of the value is 1, then we are getting the output, means it is nothing but a OR gate. So the options given are OR, AND, NOT and NOR. So the correct option here is option A, which is OR gate. Next question which we are going to see is this. What is the output of the below circuit? So this is the circuit and there is a Vin given, and this is the Vin given to the circuit. And what is the output of the circuit? There are 4 waveforms given. Which of the given waveforms is the output of this particular circuit? So if you examine the given circuit, that is this, it is nothing but a clipper circuit, and this is a series clipper. Since the resistor is connected with in series with the diode, it is a series clipper. So what it will do is it will clip off the negative half cycles from the given input waveform. So if you are giving such a sine wave to the as an input to this clipper circuit, it will clip off the negative half cycles. So it is very much evident that from the outputs, this is not the output, this is also not the output because it is having only negative half cycles. This is correct, and this is also not correct because this is having negative half cycles. So here option C is the correct answer. That is, it will keep the positive half cycles and it will clip off the negative half cycles. Okay, so this is your correct answer, which is the option C. And also, if you are going to give a square wave as an input, that is, if you are going to give a square wave as an input to this circuit, that is the clipper circuit, it will keep only this positive cycles and it will clip off the negative cycles. Okay, so this clipper circuit will clip off the negative half cycles, and the correct answer for this question is option C. The last question which we are going to discuss in this video is from diode characteristics equation. The question is, calculate the forward bias current of a silicon diode when forward bias voltage of 0.4 is applied. The reverse saturation current is 1.17 into 10 raised to minus 9 ampere and the thermal voltage is 25.2 millivolt. The correct answer you have to choose from the below options. Option A, 9.156 milliampere. Option B, 8.23 milliampere. Option C, 1.256 milliampere. Option D, 5.689 milliampere. So what is the correct answer here? So the equation for this question is, that is, you have to find the forward bias current, right? So I equal to I0, which is your reverse saturation current, into e raised to V by eta Vt minus 1. Here V is the forward bias voltage, that is V equal to 0.4 volt. Now Vt is nothing but the thermal voltage, that is 25.2 millivolt, and eta, which is the ideality factor, here it is 1, and I0 is the reverse saturation current, that is 1.17 into 10 raised to minus 9 ampere. So you have to substitute these values in this equation and find the result. To substitute the values, that is, I'm going to substitute the values here. That is 1.17 into 10 raised to minus 9 into e raised to 0.4 by eta is 1, so ignore it. Then Vt is 25.2 into 10 raised to minus 3 minus 1, right? So if you solve it, you will get the answer as option A, that is 9.156 milliampere. So this is how you have to solve this question. That is, here it is asked the forward bias current. Okay, so in order to find the forward bias current, the equation is the reverse saturation current into e raised to V by eta Vt minus 1. So here V is the forward bias voltage, that is the voltage applied to turn on the diode. Eta is the ideality factor, Vt is the thermal voltage, Okay, so if you substitute these values, you can directly obtain the result, and the result here is option A, which is 9.156 milliampere. So that's all for this video. I've tried to include maximum variety of questions from analog circuits. Analog circuits is having maximum weightage for GATE 2020. So please do prepare this session very thoroughly. Please do share this video with all your friends and family, and also don't forget to subscribe to the channel. Thank you.